Okay, so our problem is that we're going to be given a non-conducting rod of length 0.4 meters, and its total charge is 2 times 10 negative 6 coulombs, and we're also given a test charge over here. That's also 2 times 10 negative 6 coulombs, and it's placed 0.2 meters away from that non-conducting rod. So our goal here, or our objective, is to find, so A, find the electric field at the charge point, which is basically over here, and then B, find the force the charge experiences. Okay, so to find the electric field, we need to consider the main equation. So you know that electric field equals KQ over R squared, right? So that means that if we differentiate E with respect to Q, we'll get that dE by dQ is going to be equal to K dQ over, K, this K over R squared. So that means that if we multiply this to that side, a small change in electric field, or a small electric field, is produced when a tiny amount of charge is placed, right? This is just infinitesimal, so small changes. That means that we can substitute this given our charge density. So charge density is just given by this lambda. This is linear charge density. So we get that lambda is equal to our charge over, in this case, we're oriented to the x-axis. So I'll refer to this as x. It can also be like L in general. So lambda is charge density. It means how much charge is packed in a amount of space. That means if we can also rewrite lambda as a small amount of charge given a small amount of area. Multiplying dx to this side, you get that lambda times dx is equal to dq. So we need to use a charge density because we're given our charge and we're given our length, but we won't be able to figure that out just by the equation. So we make this substitution for this, for dq. So you get that dE is equal to k times lambda dx over r squared. Now, we're going to integrate both sides to find the electric field. So E is equal to the integral. We can move this k to the outside because it's a constant. K times lambda dx over r squared. So in this case, let's just move this over here. E equals k lambda dx over r squared. Okay, so in this case, what's r, right? So we have to find the electric field at this point. That means our r is going to be in terms from this initial point. So if this entire thing is 0.6 meters, r will be equal to 0.6 minus x, because anything to the left of this is going to be subtracting a change in x. Anything to the right of this will be producing an electric field of plus x. So it's going to be 0.6 minus x to find that a change in r. So we're going to substitute that over here. Also, we need to make the substitution because we're differentiating in terms of x because it's dx. So E equals k integral of lambda and then dx over 0.6 minus x squared. Now, now we can also take this out. Lambda is just a constant. Lambda is just charge over the entire length. So we can find that lambda is just our charge, or 2 times 10 to the negative 6 over our length. We can calculate this later, but let's just bring this out as well. So electric field equals k lambda integral of dx over 0.6 minus x squared. And the bounds of this integral will be from, I think it's from, yeah, it's going to be from x equals 0. So basically this, at this point, all the way to L. All the way over here. So what is the electric field that this is producing? We're going to be integrating all the little dq's that this entire rod will produce. So given this integral, we can actually evaluate this. K lambda, and this is just a simple integral, so this just becomes 1 over 0.6 minus x evaluated from L, x equals L, or yeah, to x equals 0. So we know that L is just the length of the rod, which is 0.4. So summing that in, we'll do E equals K lambda 1 over 0. So if x equals 0.4, so it's just going to be 1 over 1 over 0.2 minus 1 over 0.6. Okay, so now that we have our entire thing in terms of constants, we can make our substitutions. So we already know what k is. That's 9 times 10 to the 9th. Lambda is just this over there. So let's make our substitutions then. So once you make these substitutions, you get this is equal to 1.5, let me double check, times 10 to the, oh wait, this is actually, yeah, my bad. This is actually 6 times 10 to the negative 6. Pretty sure. Yep, this is 6 times 10 to the negative 6. So 6 times 10 to the negative 6 over 0.4, 1.5 times 10 to the power of negative 5. Now, yeah, so now we have our lambda, we have our k. So we just sub it in. 9 times 10 to the 9th times 1.5 times 10 to the power of negative 5 times this 1 over 0.2 minus 1 over 0.6. And we get that our value is approximately 4.5 times 10 to the 5th newtons per coulomb. So what do we do here, right? So first, we know that a continuous charge distribution is made up of quantized small charges, similar to this point. So what we did was we took the integral of this entire non-conducting rod and the integral of that electric field to find all of those small charges. If they sum them up together, we can actually calculate that. So that's what we did over here. And then using that, we used the linear charge density to find, to substitute that into this equation for the electric field, and find that it's 4.5 times 10 to the 5th units per coulomb. So part B is find the force that the charge experiences. So we know that force is going to just equal to our charge times our electric field. So force equals 2 times 10 to the power of negative 6 times 4.5 times 10 to the 5th. And that is equal to, 0.90 newtons, excuse me. So that makes sense, right? This charge, because it's positive, it's going to be experiencing a force to the right, which makes sense because this is also positively charged. So we know that like charges repel, so that makes sense. If our force was negative, we would have done something wrong. It should be positive because this is positive and a test charge is also positive. So yeah, that's pretty much it.